Okay, good afternoon. So today we'll continue our discussions on memory address translation. Sorry I can't give a video today because I'm not where I usually am. So we're going to just see the video, the lectures. I hope that's fine. Okay, so the last thing that the last method that we saw, so we started with BNB, and after that we discussed multi-segment address translation. So and we also discussed the downsides of multi-segment address translation, the main downside being external fragmentation. So compared to BNB, we have improved external fragmentation because now our segments are smaller than the actual application, but we still have external fragmentation. And the main reason for this is that each segment has different size. And as long as you have segments with different sizes, then external fragmentation happens, right? Because a new when a new process comes with different sizes in its segments, then there might be a chance that you have enough memory in total, but none of the free regions are big enough to fit a segment, because the free spaces that you have different sizes, and the segment that you want to allocate has a different size. So to fix this, the natural solution is to make everything to have the same size. So basically make allocations with the same size. And that's the idea behind paged memory. So in paged memory, the unit of allocation is a fixed size chunk that is called page. And we're going to page both physical memory and virtual memory. So we're going to make units of allocation to be pages. Now, the benefit of this is when your physical memory is paged, you're going to just allocate each page of physical memory to a page of virtual memory. Now, if you have one page available in your physical memory, then you can fit one virtual memory page. So external fragmentation goes away, because if you have a page available, then you can allocate it. Whereas in external fragmentation, we had available memory in total, but none of them fit the size of the segment that we wanted to allocate. And that's where we were getting external fragmentation. Now you can kind of track what pages are available and what pages are not available by just looking at a bitmap of your physical memory. So basically this bitmap here shows you can have a single bit for every page in your physical memory, and 0 could mean that this page is not allocated, and 1 could mean that this page is allocated. Now, if you want to make an allocation, you just go through this list, through this bitmap, find a bit that is 0. That indicates that this particular page physical page is not allocated, and then you can allocate it. So management becomes pretty easy. We can just do this with a single bitmap. Now you can compare this with previous method where we didn't have pages and each segment could have different sizes. Then, knowing which bytes of memory are allocated and which bytes are not allocated would be significantly more complicated. You have to, because you have different ranges of bytes that are allocated and not allocated. So a immediate benefit from having pages is just management becomes very easy. Now, the downside of having pages is it could cause internal fragmentation, depending on the size of the page. So if you have big pages, then you have less of them. Your physical memory is constant, the size of it. Now, if the size of each page is big, then you have less pages. Now, this means that when you're allocating more memory, and it could well be the case that what you're allocating is not needed by the processes that you're allocating this memory to. So this could cause internal fragmentation, where you have allocated a memory, so you cannot reallocate it to someone else, but the one that got this memory really doesn't need all of it. So we have to make a balance when it comes to the size of each page. Big pages mean lower overhead for management because we have less of them, but they could cause internal fragmentation. Smaller pages means more complex memory management, but less internal fragmentation. Typically, the size of a page is something between 1 to 16 kilobyte in day-to-day systems. Okay, now let's run an example where we're going to use this idea of page table. Actually, not an example. Let's introduce a new address translation method based on this idea of pages. Now, as I said, we're going to page both physical and virtual memory. So both of them are going to be paged. Now, the size of a virtual page, let's say if your pages are 1 kilobyte. So if you have a page that is 1 kilobyte, how many bytes do you have in your page? So 1 kilobyte is 2 to 10 bytes. So this means that you need 10 bits to address each byte in your page. So we're going to use these 10 bits in address as offset. So the offset is basically used to find a particular byte in each page. The rest of your virtual address is going to be used as page number. So this is going to be the virtual page number. Anything left is going to be virtual page number. Now, when it comes to physical address, we're going to do the same thing. So the offset is going to be the same in both physical address and virtual address because the size of the page is the same in both cases. The one that is different is this virtual page number. Now, usually we have, we have more virtual address. We have more because the size of physical address is limited. Therefore, the number of physical pages are limited, whereas the size of virtual address is huge. So we might have a lot more virtual pages than we have physical pages. So now the entire problem of translating virtual address to physical address becomes translating virtual page number to physical page number. So, as I said, depending on the size of your pages, you pick some number of bits from your virtual address as offset, and the rest of it becomes your virtual page number. Now, to translate, we need to translate virtual page number to physical page number. So we will have a table. This is called page table that maps virtual page number. It maps virtual page number to physical page number. And we're going to now add, in addition to what we've seen in the past, some permission. This permission, we could have had it in segment table as well, but I'm introducing it here. So you could have permission for each page. You could say this this virtual page is mapped to this physical page with read permission, or write permission, or read and write permission, or read only permission. And then we're going to add another bit here to indicate if this translation is valid or invalid. So if a translation is valid, it means that this mapping can be used. If this bit is set to invalid, it means that this translation cannot be used. It's invalid. So I might have used it before, but this translation no longer holds. And we'll see cases where we want to set this valid bit to invalid. So a translation might be valid now, but then later on we might actually swap a page out of memory and then make this the translation corresponding translation for this page invalid. Okay, so now let's go back to address translation. We're going to look at our virtual address, put the offset bits aside, then look at the virtual page number, go to this table. This table should be should reside somewhere in memory, right? And we probably want a pointer to this page, to this table. So operating system has to set this pointer to point to this table. Now we get the virtual page number. We probably want to check it with like page table size. We don't want to have to go and access an element in page table that doesn't exist. So we check the size. If the size is if the virtual page number is within the size of available virtual pages, then we just go to the table. We look at the translation, and we find the physical page number for this virtual page number. Then we just copy the same offset, because the offset is not going to change. We just copy as it was. We concatenate this physical page number with the offset to get the address to the particular page that we want. So this page number, points out to the page, and this offset points out to the particular byte in this page. So a particular byte that I wanted in this page, because as I mentioned, a page could be 16 kilobyte, and we might not want all of it, right? If you're doing a load, you're probably using 4 bytes. Let's say if your registers are 4 bytes, then you are only interested in 4 bytes. So once you get the page, you have to go and find the particular byte that you're interested in. For that, you use the offset. And here is your translation. Okay, so this each physical page resides in physical memory. So I think this one is the page table. So the page table also resides in memory, right? And this page table pointer is going to point to this page table where this resides. It contains physical pages, it contains a permission, and it contains the virtual page. I explained that the offset, the number of bits that we need for offset depends on the size of the virtual, depends on the size of the page, and everything that is remaining would be considered as virtual page. And that's it. Okay, so I got one question here. Is the page table stored on a per process level or for the entire system? That's a very good question. Well, the answer is each process will have its own page table, right? Because different processes could have the same virtual address. Therefore, we don't want to always translate the same virtual address to the same physical address, right? Depending on which process this virtual address belongs to, we might want to go to different places in physical memory. So each process has its own page table. Therefore, every time you context switch, you have to change this page table pointer to point to the corresponding page table for this process. Here is an example. Here I'm assuming that each page is 4 bytes. So if each page is 4 bytes, how many bits do we need for offset? Well, 4 bytes means 2 bits for offset, because with 2 bits I can address 4 bytes. So 2 bits are going to be used for offset, and the rest of it is going to be used for page number. Now, let's assume that this is your page table. So it's saying that virtual page 0 is mapped to physical page 4. Virtual page 1 is mapped to physical page 3. Virtual page 2 is mapped to physical page 1. So that's what it means. I don't know why I made this dirty and crowded, but okay. So that's the definition. So we have the page table. Now let's look at the mapping here from the virtual memory to physical memory. So let's look at an address 00 here and see where it's mapped. So we're going to put 2 bits aside for offset. So these 2 bits are offset because each page is 4 bytes. So we put 2 bits aside for offset. The rest of the bits are virtual page number. So in this case, it's 0. So we're going to go to the table and we're going to see where virtual page 0 is mapped. So virtual page 0 is mapped to physical page 4. So that would be here. Sorry, my mistake. So we have to actually construct the physical address. So the way we construct the physical address is we copy the physical page number, which is 4. So 4 is 100, right? So I copy physical page number here, and I copy the offset without changing it. The offset was 00. Now I have a different address. So this is the address that I'm going to go to memory. Now this is 0. This one is 1. So this is going to go here. So this is where page 1 is going to be mapped. Now let's look at another address here. This address is 004. So this is 0. This is 4. Again, 2 bits are going to be put aside for offset. The rest of the bits are going to be considered as virtual page number. In this case, the virtual page number is 1. So we go to the table. We look at virtual page number 1. It's translated to physical page number 3. So we construct the physical address. So this one is the 3. And this is the 0 offset that I just put here. Now, if I look at this number in hexadecimal is 0, and this one is 4 plus 2, 6. Am I mistaken? 4 plus 2, 6, no. So No, this is 8 plus 4. That's 12, which is C. So it's going to be 0, C. So it's going to go here. And then you can do the rest. And you can ask questions for yourself, so you can see where this one is mapped. So you can construct this one. I'm going to do it really quick. So 6 is 4 and 2, and then 0 is 0, 0, 0. So 2 bits for offset, the rest of them virtual page number. So what is this number? 10. 10 is 2. So 2 is mapped to 1. So if we want to construct the physical number, it's going to be 1. And then we're going to copy the offset. Now, what is this number? So this is 0. This one is 4 plus 2, 6. So it's going to go to address 06. So somewhere here. Yeah. Oh, I'm making a mistake. What was the mistake I made? Oh, sorry. So the mistake I made was this one is 8, so it should be this. Let me do it again. Sorry. So let's do it again. 0 is 0, 0, 0. 6 is 0, 1, 1, 0. So that was my mistake. So when I'm translating, I copy the offset, so no change. For the virtual page now it's 1, so it gets translated to 3. So 3 is 1, 1, 0, 0, 0, 0. So now this number is 0, and then this number is 12 plus 2, 14. So it's C, D, E, I think. Let me just make sure. Yep, it's E. So it's going to be mapped somewhere there. Okay. And so on and so forth. So you can just run examples. Okay. Now, what is, so let's focus on this page table that we talked about and see what each element of page table is. I got a question: to address all of the virtual memory, won't we need a huge page table? Yes. So absolutely. As we'll discuss, page table in this flat form is impractical. So just wait a little bit. We'll just take this idea of page table and we come up with multi-level paging. So it's going to come next. But yes, you're right. With this implementation where we have one entry per virtual page, we're going to have a huge page table, which is not appealing. So hold on to that question. We'll discuss how we can address that issue. Okay, so let's focus on the page table. Each entry, we call each entry PTE, page table entry. So this is basically a pointer to an actual page, right? It has a pointer to the actual page because it has the physical page number. It has permission bits, it has valid bit, and this the permission usually is read, write, or execute. So these are the permissions that we usually use, and any combination of them, right? So when you have a combination that grants read, write, and execute, this could be used for code or data. It was common, but not anymore. The reason is you don't want to have a piece of data that you can write and execute, because this allows the hackers to dynamically change the code and execute the same code. So it poses security risks. That's why this particular permission combination is very uncommonly used. The other combination that you could consider is read and write. This is very common. You've seen it probably for your data. You have read and write permission for your files, for example. The other common permission is read and execute. This is basically common when you have a code page, a page that is representing a binary code. You want to read it and you want to execute it. Read only is also very common when you just have read permission. For example, when your page is a library code. So all the different processes that share the library code, sorry, not library code, because library code you want to also execute. But let's say a I don't know. When you share a data that you want to keep it protected, not allowing others to change that data, you can just make it read only. Write execute is never used. Write only is used usually for device drivers. So there are certain registers in devices that are mapped to memory. So when you write to that particular memory region, you're basically writing to the registers of your device, and you cannot read from them because the device might change it, and it's meaningless. So you only provide write permission. So the device driver can just write. So this is very common when you're writing, when you're mapping device registers to memory. You just give them write permission. You could have only execute permission. It's uncommon, but if you want to have a code that you don't want people to inspect and just be able to just execute, then you have only execute permission. And if you don't grant any permission, no read, no write, no execute permission, then this could be used as a guard. For example, if you remember when we were talking about protecting the stacks for different threads, one thing that you could do, I mean, the idea was to put some guard between the stacks. So the guard could be like this. So you could just make that particular memory to have no permission. So if a thread tries to write to that that guard, then you get a notification. Okay. So permissions in action. So how can we use these permissions? So I sort of alluded to some of the use cases for different combinations of permissions, but I'm going to just talk about some of the things that we've seen, and now we can see how you can implement those ideas using the permission bits. So one of the things that you can use permissions for is demand paging. This one actually comes later, a little bit later in the course, so probably 2 or 3 sessions from now. We'll talk about demand paging, but the idea is if you have a lot of requests, a lot of demand for your physical memory, so let's say you're launching so many different processes and each one of them is consuming a lot of memory. Now you have a limited physical memory. So at some point, the physical memory is not enough to address all the demand that you have. So at that point, you might start swapping some of the pages in memory to disk so that you create a space for new demands. So this is called demand paging. When this happens, you can just use you can just change for example, the PTE for the page that you're swapping to the disk, you can just set the valid bit of that translation to invalid. So, this virtual page was mapped to this particular physical page, but now that I'm swapping this page to physical memory and giving this physical page to another process, I can just make this translation invalid. So this translation is no longer valid. You cannot use it anymore. The other one is copy and write. So this idea, we talked about it when we were talking about fork. We said that when a process forks, the new process and the old process could share the same memory. And as long as they're both reading from this memory, everything should be fine. We don't need to copy anything. So for this, you can just change the permission for both parent and the child to read only. And if any of them tries to write, then you get exceptions. And then at that point, you can just try to copy your data. Lastly, zero fill on demand. So this idea is, whenever you allocate memory to a process, to provide security and privacy, it's better to, remove any previous data that was stored in that region. Otherwise, the new process that gets this region, they can read what was written in the past by some other process, and that might compromise the privacy or the security of your system. So what you really want to do is to zero all those data before you allocate that region to a new process. Now, you don't necessarily need to do that. You only need to make them zero if the new process tries to read them. So what you could do is you could not give read permission to the new process. And the moment that new process tries to access that region to read it, you can raise an exception, and then at that point you can zero it out. So it's kind of like lazy operation. You don't make it zero at first because there is a chance that the process just writes to the region instead of reading. So in that case, you don't need to do anything, right? For example. Okay, so I guess the way in the slides that is said is that you make that make that page invalid once any access is made. Then you make that you zero that page, and you basically delay zeroing the region by this method. Okay, so another issue that we want to now check if we have, so with multi-segment memory translation, we were able to share, right? We could have had two code segments shared by two processes. The same could now happen with paging, right? So two different processes could share the same physical page. So here's an example. Let's say I have this page table that maps virtual page 1 to physical page 5 for this particular process. Now, I could, if I want this page 5 to be shared between two processes, I could potentially map it to the virtual page that I want in the other process. So I can map the corresponding virtual page in process 2 or process B to the same physical page. And this allows process A and process B to share the same memory region by just having two different translation for the same physical page. So sharing is definitely possible with this page table address translation. Here is another example. So let's assume that your pages are 8 bytes. So you need 3 bits of offset. That's what you're seeing here. So each page is 3 bytes, and the rest of the bits are used for virtual page number. Now assume that this is your page table that you can see in the middle. So for each virtual page, you have a translation if that page is allocated, and if the page is not allocated, then you have this empty cells, empty elements in your page table. So page table entries, they don't have any pointer to any particular physical page for the pages that are not translated or not allocated yet. So here is an example of a process with 4 segments: a code segment, a data segment, a heap segment, and a stack segment. Now, each segment is divided into pages. So for example, this stack segment has 2 pages, the heap segment has, I don't know, 3 or 4 pages, and so on and so forth. And each page, each virtual page is translated to a particular physical page using this page table. And you can actually check. So for those of you who want examples, so you can actually try to translate this address using this page table and see how it works. But I'm not going to do that because we've talked about it, right? So we have the offsets, we have the virtual page, and then we just go to the page table, translate the physical virtual page to physical page, and then copy paste the offset to get the physical address. So that's not the issue. Now let's assume that the stack wants to expand. In the multi-segment memory translation, the entire segment should be contiguous, should be in the same physical range, in sequential bytes in physical memory. But with page tables and the idea of paging, now I can map the additions to the virtual address space because my stack has expanded. So now I need to have 2 more virtual pages allocated to my stack. Now for the mapping, I can actually map those 2 somewhere else. I can just find 2 empty physical pages and allocate my 2 virtual pages to those. So as you can see now, my stack in physical memory has been mapped to 2 different regions. It doesn't need to be contiguous as it was with multi-segment address translation. So the first time that my application accesses, for example, this page, if the stack is going to grow, I'm going to detect a page fault because for this page, there is no translation. So this would lead to a page fault. Now the operating system is going to wake up, look at this page fault, and maybe decide that, okay, I need to allocate another page to this stack. And maybe at that point, it allocates this particular physical page. So it sets this mapping and then resumes the application, resumes the process from where it caused the page fault. Okay. Now, here is where we are going to come back to the question that one of you guys asked about the size. of this page table. So as you can see, the size of the page table is going to be huge. So we're going to have one element per virtual page. And as we discussed previously, we have so many virtual pages, right? Because the size of virtual memory is humongous. So the size is humongous, but then you divide it to the size of each page. That leads to, too many virtual pages. Now, with this idea of flat page table, I need one entry per virtual memory, and that is going to be absolutely impractical. So let's look at that. So let's discuss page table and then dive deep into the downsides, which is basically the size. Now, when a context switch happens, as we discussed, the operating system has to change this page table pointer to point to the page table of the new process that is going to run. Now, how big is the page table? That depends on the size of each page and the size of virtual memory address space. So if you have a 32-bit system, and your pages are 4 kilobytes, then so 4 kilobytes, that's 12 bits. So 12 bits for offset. That means that 20 bits are going to be used for virtual pages. Now, with 20 bits, how many virtual pages are you going to have? You're going to have 2 to 20 virtual pages. So you're going to have 2 to 20 page table entries. Let's assume that each entry is 4 bytes. Each entry in your page table is 4 bytes. That means that your page table size is going to be 4 megabytes. This is not bad, although it's huge, but it's manageable, right? So each page table is going to be 4 megabytes. That's fine, sort of. It's still huge, but sure. Let's look at a 64-bit system. So with the same number of same size for physical page or for your pages, so 12 bits for pages, that leaves you with 52 bits for virtual pages. So you have 2 to 52 virtual pages. Let's say each one of them is 8 bytes. Then you have 32 petabytes. You need 32 petabytes to just store your page table. So if you have a 30, like if you have 30, let's say max, let's say you have 64 gigabytes of physical memory, to just fit a page table, the entire physical memory cannot fit a single page table because the size of the page table is 32 petabytes. So this shows us that this is not going to work, right? This is impractical. Having these huge page tables is not going to work. Okay, so what are the upsides of page table? Well, it's simple. It simplifies memory allocation, right? It's very easy to share memory, as we saw, between different processes. The downsides, the main downsides is the space. So it requires a lot of space, as we just saw in this example. Now, one thing that you could do to, maybe kind of resolve this issue is maybe you should make your pages to be bigger. Instead of 4 kilobyte pages, you might have, I don't know, 1 megabyte pages. That could save you some. It could reduce the number of virtual pages that you have, but it's not going to address the actual issue. So before I jump into how we can address this issue, let me go back to this slide here. One thing that I want you to note is these virtual pages here are empty, right? We're not using these virtual pages. And, you know, it's not obvious in this figure, but this is huge, right? The number of virtual pages that we're not using is huge. You know, this is 2 to 60, this could be 2 to 64 bytes, which is like, as we saw, is like a huge, virtual address space. How much is your code? Your code is usually a few kilobytes, or let's say like the 1 or 2 megabytes of code. Your data is potentially a small, I mean, worst case scenario, let's say you have gigabytes of data, might happen if you're, you know, maybe training a neural network or something. But the data is also limited. Heap is limited. A stack is limited. So if you add it up, let's say you have a Hello World program. Your Hello World program is a bunch of kilobytes. The entire process is going to be a few kilobytes at most. Most of our programs, most of our processes are small, so they're not using their entire virtual address space. So this means that a lot of these virtual pages are not used. With page table, even if we're not using those pages, we need to keep an entry for them. Each virtual page has to have an entry. And because we have so many virtual pages, then we will have huge page tables. So we need an idea that allows us not to store page table entries for virtual pages that we're not using. So that's where we're going to go. So we're going to make it so that for the virtual pages that we're not using, we don't need to use a lot of page table entries. So that's the goal now, to do an optimization to achieve this goal. Okay, so keep that in mind when we start talking about the solution for reducing the size of this page table. Okay, so the idea is, if you want to reduce, if you want to eliminate the problem of having to store page table entries for pages that you're not using, the idea is, instead of representing your page table as a flat table, and by flat I mean I have one entry for each virtual page, you can move on to multi-level pages. You can represent your address space using trees instead of linked lists. So it's kind of like that, right? Because the page table we just saw is flat. It's kind of like a linked list. So instead, we're going to use trees to have less memory footprint for our page table. Without further ado, let's talk about two-level. Let's start with two-level page table address translation. So the idea is, I'm going to store, so the number of bits that I'm going to use for my offset is not going to change. Now, I'm going to divide the number of bits that I have left for my virtual page to two portions. So I'm going to have, let's say this is a 32-bit system, and let's say each page is 1 kilobyte. So I need 12 bits. Sorry, this is 4 kilobyte. So 4 kilobytes. So I need 12 bits. Now the rest is 20 bits. So 20 bits are left for virtual page number. I'm going to divide them into two portions. So 10 bits I'm going to use for virtual page index 1 and 10 bits for virtual page index 2. Now, when I'm translating, what is going to happen? I'm going to take the first index and go to my first level page table. Now, how many entries do I need here? Well, I need 2 to 10 entries here, 2 to 10. So compare that, if I wanted to have a flat, I would have had one page with 2 to 20 entries. Now, because I cut it to 10, now I only need 2 to 10 entries, right? Now this, let's say I find the entry corresponding to this virtual page index 1. Now this is going to point to another table. So this entry is going to point to another table. Then I'm going to use this, and any other entry in this first level page table is going to point to another table. So for each entry, I will have another table. Now, I will use the second 10 bits of my virtual index, and I use that to index into the table that was pointed to by the first level page table entry. Now here I will find, so how many of these now we have? 2 to 10. Because I have 10 bits left, so I can access or address 2 to 10 entries, right? So then I use virtual page 2 index to find the entry in the second level page, and that gives me the physical page number. So now I found my physical page number. So I did 2 accesses instead of 1. With the page table, I would just use the virtual page and use that as an index. I would go to my page table and I would find my physical page number. Now in this one, I have 1 level of indirection. So I first used the first 10 bits. That gave me an address to another page table. Then I used the second 10 bits to index into that second page table to then find my physical page number. And then I copy the offset, and this gives me the page in physical memory. So that's 2-level page table. Okay, now let's discuss this. So again, in each page table entry in second level page table points to a physical page. So each page table entry in first level points to another page table, and then each page table entry in the second page table then points to a physical page. So this is page table level 2. This is page table level 1. And the last one is just actual page. Okay. So each, as I mentioned, in this particular example, each page has 2 to 10 entries, so 1024 entries. Now, how are we saving a space, you might ask? So why is this better than flat page table? How are we saving anything here? How are we saving the the space for our page translation? The way we're saving is, if a page table entry here in first level page table is not valid, so if it's not used, then it does not point to any page table level 2. Therefore, I'm not gonna use any memory for page table level 2 for the entries that are invalid here. So for any entry that is not used here, I'm saving 10 to 20. I'm saving 2 to 10 page table entries, right? For any one of these, I'm saving this much page table entries. Now each one of these could have 4 bytes. So in total, I'm saving this many bytes. This was not true with flat, right? With flat page table, if an entry was not used, then the corresponding physical page was not used. So that was it. Here, in this tree representation, if a page table entry level 1 is not used, I'm not going to allocate any memory for a page table level 2. And by that, I'm saving these many entries. And that's how I'm saving, right? So here is the example. The same example that we saw in the flat page table translation. Now, again, let's say each page has 8 bytes. So I need 3 bits for offset. That leaves me with 5 bits for virtual page number. Now, let's assume that we're going to cut or divide it into the first 3 bits are going to be used for virtual page level 1, and then 2 bits are going to be used for virtual page level 2. Okay, now if I look at these, if I want to have my first page table, so page table level 1, so this is page table level 1, how many entries do I need? 2 to 3, because I'm using 3 bits for virtual page number 1. So I need 2 to 3 entries. So that these are the entries here, as you can see. I'm going to have 8 entries for 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way to 1, 1, 1. Okay, now after that, I'm going to look at for any of these. Now, how many of these pages am I using? So if you look, I'm using number 8. Sorry, that's 7. 1, 1, 1, that's 7. I'm using this guy, which is 6. I'm using this one, which is 4. I'm using 2, and I'm using 0. So from the 8 entries, I'm only using 1, 2, 3, 4, 5. So 3 of them we're not going to use. Am I making a mistake here? Oh, sorry. This one is not used. What am I doing? So 6 is not used. So 6 is pointing to empty space. Sorry. So yeah, I'm like, why is this happening? So this free space, I'm not using it. So all I'm using is 0, 2, 4, and 7. So 4 of these entries are used, and 4 of them are empty. So as you can see, I have 4 empty regions here. I'm not using them. So I don't need to allocate page table level 2 for these. For the ones that I'm using for 1, 1, 1, I have page table level 2 for 1, 1, 1. I have page table level 2 for 1, 0, 0, 0. I have a page table level 2 for 0, 1, 0. And I have a page table level 2 for 0, 0, 0. Now, how many entries each one of these going to have? Well, I'm having 2 bits, so it's going to be 2 to 2, which is 4 entries. So each page table level 2 needs 4 entries, and which is what you can see. Okay, so that's the example. And where are we saving a space for our page table? Well, for all these null entries in page table level 1, I don't need to allocate page table level 2. So those are the entries that I don't need to represent. So that's where I'm saving a space. Okay, so I got 2 questions here. Let me answer. Does the 2-level page table introduce overhead to make second level page and remove them as needed? So the overhead is really not adding or removing them, because probably we're not going to add or remove much. The overhead is, previously for each translation, we needed to go to memory once, right? So if I had the virtual page number, I would just go to my page table, and going to page table means I'm going to read from memory, and I would read the translation of this, and then I have the physical address, then I go and read my my physical bytes, whatever I wanted to read. So for each translation, I needed to go to memory once to translate. Now with this one, I need to go to memory twice. So I have to first go to page table level 1 to get to read that. And after I read that, then I have to go to page table level 2 for a second read. And then I have my physical memory translation. So the overhead is the number of times that I'm going to go to memory to translate my my virtual page number to physical page number. In the flat representation, it was just 1. In 2-level, it's 2. So that's the overhead, and it's going to be a problem that we will have to resolve next. Okay, so another question. In the second level table example, how are we saving 4 bytes for each of the 2 to 10 entries? Won't the page table just have the address of the physical memory plus permission bits? How would that lead to 4 bytes for each page table? Right, so that's a good question. Now, the number of bytes that you need for each page table entry depends on your available physical memory as well, right? Because you're going to have your physical page number there. Now, if you have, let's say, if you have, I don't know, you might need 20 bits, for example, for physical page number. So how many bits you need just for physical page number might be 20 bits. It will depend on the size of your physical memory, right? You might have 2 to 20 physical pages. Now, your page table entry should have at least 20 bits for this translation. And then add to that the permissions, the valid, invalid, and some other bookkeeping bits that you might need per page table entry. We actually will talk about page table entry in x86. So we'll talk about what kind of data is stored in each entry. But it's usually for 32-bit systems, it's 4 byte, and for 64-bit systems, the size of each page table entry is 8 byte. Again, we'll come back to that. Just in a little bit, we'll discuss that. I actually don't know if it is here, if it's in this slide deck or in demand paging, but we'll talk about it in the future. Okay. Hopefully I answered that question. Okay. Okay, so you can actually look at how this memory is translated. Looking at this, this is virtual page level 1, virtual page number 3 in page level 1. So you go here, you look at the corresponding page table level 2. So you're going to go here. Then you're going to use the second 2 bits 1, 0 to get your physical address. Once you have your physical address, you're going to append to that 0, 0, 0 to get your physical address, and then that's where you're going to go in your physical memory to get the data you want. So as I said, this requires 2 accesses to memory to do the translation so that you can finally go and read or write to or from your physical memory. So the benefit of this is now the number of page tables that I'm using is proportional to the number of pages that I'm using, right? So as I said, the number of virtual pages that my program uses is usually limited. So I kind of have reduced the number of page table entries that I need to be proportional to the number of to the number of virtual pages that I'm using. This was not the case with the flat representation, because in the flat representation, I didn't care how many virtual pages I'm using. My page table size was always as many virtual pages I have, not as many as I'm using. But now, you know, for all the pages, virtual pages that I'm using, I have a page table entry with a little bit of overhead, which is this page table number 1. So it's not exactly the same as the number of virtual pages that I'm using, but it's approximately the same. So that's huge saving in the size of my page table. Now you can combine the idea of segmentation and pages. So you can have a multi-level address translation that instead of having 2-level pages, you can have 1 level to represent your segment, and then another level to represent the pages inside that segment. So instead of you arbitrarily cutting your virtual page number to 2 different page numbers, you can use some number of bits from your virtual address as segment number, and then the rest of it as page number within that segment. So that's the idea. So it's very similar to 2-level paging. So now I use some of the bits as my segment number, the rest of them as virtual page number, and the size of the offset depends on how big my pages are, as before. So then I will have a segment map as before, which I'm going to use to translate segment number to a page table. Then I use the virtual page number to index into this page table to then translate and find the physical page number. So once I have the physical page number, I just append it with the offset, and this gives me the physical address that I need. And I can just do the checking, for example, in this particular example, with granularity of pages. So on each page, I can have permission and valid versus invalid. You could also put permissions here so that you enforce permissions at the level of segments. So you could say for all the segments, code segments, for example, it's read and execute, no write. for example. So you have you can put the permissions here and here, or just for pages. At least you need it for pages, right? So that's another thing that you can actually add or remove to your design. Okay, so I got another question here. What does the 4 bytes on the widths of page table entry mean? So that means how large is each page table entry, as I discussed. So if I'm not mistaken, you're asking about this. So this 4 byte here means how large is each page table entry. And we'll, as I said, we'll discuss. It has to be as large as, it's going to point to somewhere in memory, right? So this is this guy is a pointer to some memory because it has the physical page number, right? So if your memory is, let's say, I don't know, if you have 4 GB, you have to have enough bits here in your page table entry to be able to address particular memory regions. So that's why each page table entry has its size. So it has to have a size. Okay, so when a process needs additional allocated page table, how do we find the available addresses in physical memory to be added for the new table? Well, that happens by the operating system, right? Operating system tracks which physical pages are allocated. So looking at that bitmap that we discussed, operating system knows which pages are available, which pages are allocated, and then operating system could allocate new pages to contain new page tables, right? Because these page tables, these guys, are going to be stored in physical memory. So they're going to be stored in some physical page. So operating system looks at available pages, allocates them to page tables, and then sets these page table entries to point to those newly allocated page tables. The other question I got, what does the 4 byte on, oh, never mind, reviewed the slides and lecture again and got the answer. Okay, good. Okay, so moving forward. So what do we need to save in this particular design if we context switch? Well, we need to save the content of both of these two. So you probably want to have a if this segment map. So depending on how you implement, so for example, in x86, this segment map has its own registers. So you just you need to just save the registers in this segment map. If in your design you don't have registers and you're saving it in memory, then you probably have to have a register that points to this segment map. So then the content of this register you have to save, and that's pretty much it, because this page table is in memory. So if this segment table is also in memory, then all you need to save is this particular register that points to this segment map. If the segment map is itself a bunch of registers in the hardware, then you have to save them all, so that when you come back, you can fill the segment map again with whatever you had before context switching. Okay, now I kind of alluded to the fact that x86 uses this multi-level page segmentation. So In x86, you have this global descriptor table, which is similar to this segment table. So basically these are a bunch of registers in the processor that constitute the global descriptor table. It would point then to page tables for each segment, very similar to what we saw. And they have segment length, so each segment could have length. You have segment access permissions. So in x86, each segment has its own permissions. As I said, for example, for your code, you can give your entire code a read and execute permission. Now, whenever you do context switching, you just need to save this global descriptor table register. So there is a register. So there is a single register that points to this global descriptor table. So this guy is in memory, and now you have a register that points to it. So you save it, and this page table here, this is your segment table. It points to a first level page table. Then this guy points to another page table. This guy points to another page table, and this guy points to another page table. And eventually you get your physical. So there are 4 levels of indirection, if I'm not mistaken. So you have a multi-level page table. So in a 32-bit system, you have 2 levels. In a 64, you have 4 levels of page tables. So here's the demonstration for a 32-bit system, x86. So this is 32 bits. It assumes here that each page is 4 kilobyte. So 12 bits are used for indexing. 10 bits are used for page table level 2. 10 bits are used for page table level 1. You might now ask, where is the segment number? So segment numbers, each one of them have its own register. So in x86, it's kind of like appending this 32 bits plus the register. So you usually have a stack segment or code segment or data segment registers that you will use to save the address, to save your segment number, right? So it's kind of like appending the virtual memory by adding these segment registers. And on context switch, you have to save these segment registers. Each page table entry is 32 bits. In x86, 64-bit virtual address. Again, for 4 kilobyte pages, you need 12 bits for offset. Then you have 4 levels of page tables instead of 2. So 9, 9, 9, 9. So each one of them uses 9 bits. In 64-bit system, the design choice was for each page table entry to be 64 bits rather than 32 bits. So the size of each page table entry is 8 bytes. One thing I want to mention is in x86, at least in Linux and almost all other operating systems, bits from 48 to 63 are not used, actually. So these are basically not used. So in essence, you have 2 to 48 addressable bytes. These are reserved. These are not used. So in new designs, as our systems evolved, we might start using these bits, but as of now, we're not using them. So this by itself is plenty, 2 to 48. Okay, so let's let's do some math, a little bit of math. So the page table level, each page is 4 kilobyte. Now, the page table level 4, how many entries does it have? It has 2 to 9 entries, and each entry is going to point to a physical page that has 4 kilobyte. So basically what I can say is each page table entry is pointing to 4 kilobyte. The entire page table is pointing to 2 to 9 pages, and that's basically 1 megabyte. Now, if I go to level 2, I have 2 to 9 entries, and each entry, as we saw, is going to point to a page table, and that page table is going to address 1 megabyte. So that's 2 to 9 times 1 megabyte. Sorry, this one is 2 megabytes. So 2 to 9 times 2 megabyte, this is going to be 1 gigabyte. So page table level 2 is going to cover 1 gigabyte of data. And as you can see, moving forward, this one is going to cover 2 to 9 times 1 gigabyte of data. And then the last one is going to be 2 to 9 times 2 to 9 times 1 gigabyte. So the coverage is growing this way. So I'm going to stop here. So we'll continue discussing this on Thursday. Thank you for sticking around. We'll talk to you on Thursday. Take care, be safe, bye.